Hello students, welcome to lecture 9 on estimation theory 1. In this lecture, I will discuss the basics of estimation theory and some of the important properties of estimators. Let us start with introduction. We discussed the modeling of random data in terms of their joint PDF or PMF in the case of discrete. We have to fit this joint PDF from the observed data. Assuming the nature of the joint PDF, suppose we know the nature, what is the PDF, and there is an unknown parameter theta, we have to determine the base value for this unknown parameter theta. So, that way estimation comes. For modeling random data by a WSS random process, we have to determine the value of the autocorrelation function at different legs. Therefore, estimation of autocorrelation function is to be done. For fitting an ARMA models discussed in the last lectures, we have to find the base values of the model parameters from data. This is again a case of estimation of the model parameters. We may have to determine the correct value of a signal from the observed noisy data. So, noisy signals from the observed noisy signals. So, that way this is also case of estimation of signal from noisy observations. All the above cases are examples of application of the estimation theory. Particularly, this is an example of signal estimation, and these 1, 2 and 3 are examples of parameter estimation. And we can do also signal estimation by using parameter estimation. For example, by fitting the ARMA model, we can estimate a signal. So, that way estimation includes two classes, parameter estimation and signal estimation. We will discuss the problem of parameter estimation first. Parameter estimation. We have a sequence of observed random variables x1, x2 up to xn. There are n random variables represented by a random vector. This is the representation. It is represented as a column vector, and which we can write as the row vector transpose. So, that way observed data are modeled as random variable. Now, particular values of the observed data, what we observed? The observed data vector small x vector, that is small x1, small x2 up to small xn transpose, is a realization for the samples of x, because x is a random vector and whatever we observed at a particular time, this constitute a realization for the sample of x. So, small x is a realization, big X, capital X is a random vector. Sometimes we consider xi to be IID, that is also one important concept, independent and identically distributed. All x1, x2 and xn are independent and each of them will have the same distribution. X is characterized by a joint PDF which depends on some unobservable parameter theta given by this. We can write the joint PDF in terms of a parameter theta, and this in the vector notation we will write like this, and we will omit this x also. So, this will be simply f of x theta. Now, what is an estimator? An estimator theta hat x, that is equal to theta hat x1, x2 up to xn, is a rule by which we guess about the value of an unknown parameter theta. So, we will guess about the unknown parameter theta using this rule. It is a function of the random variable x1, x2 up to xn, and it does not involve any unknown parameters. This functional relationship does not involve any unknown parameter. Such a function is generally called a statistic. So, an estimator is a statistic. Being a function of a random variable, theta hat x is also random. So, that way this is a random variable, theta hat x is a random variable. For a particular observation x1, x2 up to xn, we get what is known as an estimate, not estimator, of the parameter theta. Thus, when we consider in terms of random variable theta hat x, that is equal to theta hat x1, x2 up to xn is an estimator, and theta hat of small x vector, that is theta hat small x1, small x2 up to small xn is an estimate. So, this we have to distinguish an estimator and estimate. Let us give an example, example 1. Let x1, x2 up to xn be a set of independent normal mu 1 random variable with unknown mean mu. For this normal distribution, mu is unknown. The joint PDF of x1, x2 up to xn is given by, this is the joint PDF, and that will be product of individual marginal PDFs. So, that way product I going from 1 to n of 1 by root over 2 pi e to the power minus half of xi minus mu whole square. So, using the property of exponential function, we can write it in terms of a sum here. So, this is the joint PDF of data, and here unknown quantity is mu, and if we take mu hat is equal to 1 by n summation xi, I is equal to 1 to n, it is an estimator for mu. It does not involve any unknown parameter, and it is a function of these random variables. So, it is an estimator for mu. But the question will arise how we can get such an estimator. Example 2, this is a practical example. Suppose we have a DC voltage theta corrupted by noise Vi, and the observed data xi, I is equal to 1, 2 up to n are given by xi is equal to theta plus Vi. Now, we assume that Vi's are independent and each is distributed as normal 0 sigma square. It is 0 mean sigma square is the variance, because xi is a sum of theta plus Vi, this is 0 mean. So, xi's are IID and it is normal theta sigma square random variables. So, it is normal distribution with mean theta and variance sigma square. Then again, since it is a normal distribution, this theta hat is equal to 1 by n summation I going from 1 to n of xi is an estimator for theta. Let us discuss the desirable properties of an estimator. A good estimator should satisfy some properties. These properties are described in terms of the mean and the variance of the estimator. First, we will discuss unbiased estimator. An estimator theta hat of theta is said to be unbiased if and only if E of theta hat is equal to theta. Unbiasedness means that on the average the estimator gives the true value of the parameter. So, on the average estimator gives the true value of the parameter. It is a desirable property. Now, if it is not an unbiased estimator, suppose theta hat is not an unbiased estimator, then B of theta hat, that is equal to E of theta hat minus theta, is called the bias of the estimator. So, this quantity, this difference between expected value and the true value is called the bias of the estimator. It is desirable that B theta hat decreases as n increases. Eventually, it should go down to 0. Theta hat is said to be an asymptotically unbiased estimator if limit of E theta hat as n tends to infinity is equal to theta. So, as we have large number of data, then theta hat, E of theta hat will become close to theta. Unbiasedness is necessary but not sufficient to make an estimator a good one. We have to consider other properties. We will give another example, example 3, example 2 revisited. Suppose we have a DC voltage theta corrupted by noise Vi and the observed data xi, I is equal to 1, 2 up to n are given by xi is equal to theta plus Vi. If Vi's are 0 mean, then E of xi will be equal to E of theta plus E of Vi is equal to theta. For theta hat, that is equal to 1 by capital N summation xi I going from 1 to n, that is the estimator we are considering. E of theta hat will be equal to 1 by n into summation I going from 1 to n of E of xi. Now E of xi is equal to theta, therefore this will be equal to 1 by n into n theta, that is equal to theta. Therefore this theta hat is an unbiased estimator of theta. We will consider another example. This is the estimator for variance. Suppose x1, x2 up to xn are IID, independent and identically distributed, and we have two estimators for sigma square. Sigma square is the variance. There are two estimators. One is sigma 1 hat square, that is equal to 1 by n summation I going from 1 to n of xi minus mu hat whole square. So this is one estimator, and second estimator is same as this summation, but that scaling is 1 by n minus 1 and here 1 by n. So that way we have two estimators, sigma 1 hat square and sigma 2 hat square. We can show that this estimator sigma 2 hat square is an unbiased estimator, but this is not an unbiased estimator. For this, we will consider what is E of xi minus mu hat whole square. First we will determine that E of xi minus mu hat whole square I going from 1 to n, that we will write in terms of mu. So that way xi minus mu plus mu minus mu hat whole square. So this quantity now we can expand. First term will be E of xi minus mu whole square. The second term will be E of mu minus mu hat whole square, and then cross terms will be there twice, E of xi minus mu into mu minus mu hat. So I know that this is IID, so that way there will be n such terms because of this summation. So we can write this expectation is equal to, first term will be n sigma square and second term will be summation of this quantity E of mu minus mu hat whole square, and third term will be summation of this quantity E of xi minus mu into mu minus mu hat. So let us see what is this term equal to. So this is E of mu minus mu hat whole square. This expression is important for us. So E of mu minus mu hat whole square, that is the variance of mu hat, is equal to E of mu minus summation xi by n whole square. So if I take n common, then because of this square, E of n mu minus summation xi whole square divided by n square, and this we can write as E of summation xi minus mu whole square divided by n square. Now this is again a summation. That summation we can write in terms of the individual square terms, E of summation of xi minus mu whole square, and then all cross terms we have to consider, because these are cross terms, xi minus mu into xj minus mu in this form. Therefore joint expectation of these quantities will be 0 because of independence. Xi and xj are independent, therefore this expression will become 0. So therefore this will be simply E of summation of xi minus mu whole square divided by n square, and this is equal to sigma square by n, because each is identically distributed, therefore variance will be same for all xi's, and this term will be equal to E of xi minus mu whole square will be sigma square. So that way we will get n sigma square here divided by n square, that way it will be sigma square by n. So this is an important observation, therefore this quantity E of mu minus mu hat whole square is equal to sigma square by n. This result will be used later on also, we have to remember this result. And similarly we can show that E of xi minus mu into mu minus mu hat. Now mu hat will involve all the random variables, but only in the case where it is xi, then only this expectation will become non-zero, otherwise this expectation will become 0. So that way this expression will become minus sigma square by n. Therefore we have to determine this expression E of summation xi minus mu hat whole square I going from 1 to n, this is equal to n sigma square, then this term plus this term. So we can write this as E of summation I going from 1 to n of xi minus mu x hat square is equal to n sigma square plus sigma square minus 2 sigma square. So that way it will become n, because this is sigma square, this is minus 2 sigma square, so that way it will become n minus 1 sigma square. So this will imply that, so now if we have to find out the E of sigma 1 hat square, that is scaling factor is 1 by n into this quantity, so that way it will become n minus 1 divided by n into sigma square. So this is not equal to sigma square. So this is not equal to sigma square. So if I consider this E of sigma 1 hat square, that is not equal to sigma square, therefore it is not an unbiased estimator. But if we consider sigma 2 hat square, that is equal to 1 by n minus 1 into E of summation xi minus mu hat whole square, that is equal to sigma square. Therefore sigma 2 hat square, that will be unbiased estimator. So sigma 2 hat square is an unbiased estimator of sigma square, while sigma 1 hat square is not. That is why in determining the sample variance, we always divide by n minus 1 to make it an unbiased estimator. But as n tends to infinity, this quantity will become 1, as n tends to infinity, this quantity will become 1. Therefore sigma 1 hat square is asymptotically unbiased. So we consider the mean of the estimator, we will consider the variance of the estimator. The variance of the estimator theta hat is given by this. Variance of theta hat is equal to E of theta hat minus E of theta hat whole square. That is the variance. This is the random variable and its mean. So that way this is the variance. For the unbiased case, this variance of theta hat will be simply E of theta hat minus theta whole square, because E of theta hat is equal to theta. The variance of an estimator should be as low as possible. An unbiased estimator theta hat is called a minimum variance unbiased estimator MVUE if E of theta hat minus theta whole square, that is variance of theta hat, is less than equal to E of theta hat dash minus theta whole square, that is variance of theta hat dash. So variance of theta hat is less than equal to variance of theta hat dash, where theta hat dash is any other unbiased estimator. So we discussed mean variance, another term mean square error MSE. MSE is equal to E of theta minus theta hat whole square. Minimizing the MSE is an important estimator criterion. MSE should be as small as possible. out of all unbiased estimators, the MVUE has the minimum mean square error. So, in the case of unbiased estimator, MVUE will have the least MSE. Now, MSE is related to bias and variance as shown below. MSE is equal to variance of theta hat plus bias of theta hat square. This we can prove easily. MSE is equal to E of theta hat minus theta whole square by definition. That is equal to, now we can write E of theta hat minus E of theta hat plus E of theta hat minus theta square. We are subtracting E of theta hat and adding E of theta hat. Now we expand it, E of theta hat minus E theta hat whole square, E of E theta hat minus theta whole square plus twice AB term 2 of E of theta hat minus E theta hat into E of theta hat minus theta. Now this term, first term is the variance of theta hat, and second time, because it is a constant quantity, it will remain as E of theta hat minus theta only, and therefore, this quantity will be simply bias of theta hat square. And the third term, because E of theta hat minus E of theta hat, that will be same as E of theta hat, because this is a constant quantity. So, this term will become 0, therefore, this term will become 0. Therefore, what we get, MSE is equal to variance of theta hat plus bias of theta hat square. This is one important relationship, and when this quantity will become 0, bias 0, unbiased case, in that case MSE is equal to variance of theta hat. Now, we will discuss consistent estimators. As we have more data, the quality of estimation should be better. This idea is used in defining the consistent estimator. So, this estimator is a good estimator if we have large amount of data. An estimator theta hat is called a consistent estimator if theta hat converges in probability to theta. So, convergence in probability, that is defined in this way. So, this is the limit as n tends to infinity of the probability of mod of theta hat minus theta greater than or equal to epsilon. So, that means probability of the deviation as n tends to infinity, that should go down to 0 for any epsilon greater than 0. So, that way we have defined a consistent estimator. Thus, a consistent estimator converges to the true value of theta in probability. Less rigorous test, because here we have to determine the probability. So, there is a less rigorous test is obtained by applying the Chebyshev inequality. Now, probability of this deviation is less than equal to E of theta hat minus theta whole square, that is nothing but the MSE divided by epsilon square. So, therefore, if this quantity will be 0, then this probability will also become 0. Therefore, if limit of E of theta hat minus theta whole square as n tends to infinity is equal to 0, then theta hat will be a consistent estimator. So, this is the consistent estimator, this is the test for consistent estimator we will be using. Now, if theta hat is unbiased, in that case MSE is same as variance of theta hat. Thus, if the estimator theta hat is unbiased and variance of theta hat goes down to 0 as n tends to infinity, then theta hat will be a consistent estimator. Note that consistency is an asymptotic property. As we get more and more data, the estimate become better and better. That is the concept behind consistent estimators. Let us consider one example. Xi up to xn are IID with unknown mu and known variance sigma square, and suppose mu hat is equal to 1 by n into summation xi I going from 1 to n. So, E of mu hat will be equal to summation E of xi divided by n. So, that way it will be mu. So, that mu hat is unbiased. Variance of mu hat, now this variance we have that is equal to variance of mu hat is equal to E of mu hat minus mu whole square. That we have already determined in our example 4. So, that way this will be equal to simply sigma square by n. So, variance of mu hat is equal to sigma square by n, because xi are IID. So, as limit n tends to infinity, this variance will become 0. So, limit of variance of mu hat as n tends to infinity, that is equal to limit of sigma square by capital N, n tends to infinity, that is equal to 0. Therefore, mu hat is a consistent estimator of mu. So, that way sample mean is not only unbiased, but it is also consistent. That means, if we have more and more number of data, then variance will go down to 0, and we will get the true value of the mu. So, that is the idea behind consistent estimators. We will introduce another term, efficient estimator. Suppose theta 1 hat and theta 2 hat are two unbiased estimators of theta with variance of theta 1 hat less than variance of theta 2 hat. This is a better estimator. The relative efficiency of estimator theta 2 hat with respect to estimator theta 1 hat is defined by this ratio, variance of theta 1 hat divided by variance of theta 2 hat. This variance is less, therefore, this number will be less than 1. Particularly, if theta 1 hat is an MVUE, then theta 1 hat will be called an efficient estimator, and the absolute efficiency of an unbiased estimator with respect to this estimator. So, this is relative efficiency, but absolute efficiency of an unbiased estimator will be determined with respect to the MVUE. So, here this will be the estimator with minimum variance. Then we will call this efficiency as the absolute efficiency. We will give another example. Suppose x1, x2 up to xn are IID random variables with unknown mu, and mu hat and mu 1 hat are two estimators of mu given by mu hat. This is the sample mean as usual, and mu 1 hat, suppose we define, that is equal to half of x1 plus xn. Now, both are unbiased estimator, and we see that variance of mu hat, this quantity sample mean is equal to sigma square by n, and we can show that using the same formula, n is equal to 2, variance of mu 1 hat will be equal to sigma square by 2. Therefore, efficiency, relative efficiency of mu 1 hat will be 2 by n. If I consider the ratio of this quantity divided by this quantity, then we will get 2 by n. So, this is the relative efficiency of estimator mu 1 hat with respect to mu hat. Let us summarize. The observed random data x1, x2 up to xn, these are random variables, are modeled as random variables and are characterized by a joint PDF which depends on some unobservable parameter theta. An estimator theta hat x, that is equal to theta hat x1, x2 up to xn, is a rule by which we guess about the value of the unknown parameter theta. An estimator theta hat of theta is said to be unbiased. We introduce what is an unbiased estimator. So, unbiased if and only if E of theta hat is equal to theta. Unbiasedness means that on the average the estimator gives the true value of the parameter. It is a desirable property. Theta hat is said to be asymptotically unbiased if limit of E theta hat as n tends to infinity is equal to theta. Then we discussed about MVUE. An unbiased estimator theta hat is called a minimum variance unbiased estimator MVUE if variance of theta hat is less than equal to variance of theta hat dash. So, where theta hat dash is any other unbiased estimator. So, in the case of MVUE, variance is the least, minimum variance unbiased estimator. We also discussed about the mean square error MSE of an estimator given by MSE is equal to E of theta minus theta hat whole square. MSE is related to the variance and bias by this relationship. MSE is equal to variance of theta hat plus bias of theta hat square. Then we defined consistent estimator. An estimator theta hat is called a consistent estimator of theta if theta hat converges in probability to theta. Thus, what we have limit n tends to infinity of probability of the deviation theta hat minus theta greater than equal to epsilon is equal to 0 for any epsilon greater than 0. So, for any epsilon greater than 0, if probability of this deviation goes down to 0 as n tends to infinity, then the estimator will be consistent. If the estimator theta hat is unbiased and variance of theta hat go down to 0 as n tends to infinity, then theta hat will be a consistent estimator. This is a test for the consistency of an unbiased estimator. Variance of theta hat should go down to 0 as n tends to infinity. The relative efficiency of an estimator theta 2 hat with respect to theta 1 hat, which has lower variance, is given by relative efficiency is equal to variance of theta 1 hat divided by variance of theta 2 hat. Thank you.